Okay. Hello everyone. Welcome to Nice Talk today. This is the 102nd talk from Nice, and welcome everyone to join us on Saturday evening, which is actually Saturday night in New York time. And today, let's welcome our speaker, Yueqi Song. She is a first-year PhD student at CMU, and her advisor is a very famous Graham Newbigg. And her research direction is open source autonomous agents. So today she will talk about her latest research, collaborating with a bunch of academia plus industry collaborators on agent data protocol, unifying datasets for diverse, effective fine-tuning of LLM agents. So
Recording in progress.
Let's welcome Yueqi and let her share the screen.
Hi everyone, my name is Yueqi. I'm a first-year PhD at CMU. I'm advised by Professor Graham Newbigg, and today I'll be talking about our work on the Agent Data Protocol, or ADP in short. This is joint effort with an amazing group of collaborators from CMU, OSU, HKU, Duke, Fujitsu, and All Hands AI. So maybe as a short summary of the paper, the core idea of this paper is simple to state. There is already a lot of agent training data out there, but it's currently fragmented across heterogeneous formats, tools, and interfaces. So because of this fragmentation, large-scale supervised fine-tuning of large language model agents is still surprisingly rare in public research. Our proposal in this paper is to introduce Agent Data Protocol, a lightweight representation language that acts as an interlingua between diverse agent datasets and unified agent training pipelines downstream. ADP is expressive enough to capture API and tool use, browsing, coding, software engineering, and generic agentic workflows, while remaining simple to parse and train on without per dataset engineering. In this talk, I will first motivate why agent SFT is still hard in practice, and then describe ADP's design principles and schema, and finally show experiments where we convert 13 existing datasets into ADP format and build a 1.3 million trajectory corpus and get around like 20% average gains over base models across SweetBench, WebArena, AgentBench, and Gaia. Let me start with the good news. We already have abundant agent training data across coding, software engineering, web browsing, and tool use. There is now like a total of 1.3 million training trajectories available from public datasets that we are utilizing. So these include datasets like Agent Instruct, Code Feedback, Code Act Instruct, Mind2Web, SweetDream, SweetSmith, etc. So the bottleneck here is not the absence of data. The bottleneck is that this data lives in many different formats and action spaces, which makes it really hard to combine and reuse across agent frameworks. So, the question here is, why isn't agent SFT already common in academic research? Despite abundance, like large-scale supervised fine-tuning of agent is still rare in academic work. A few projects have shown that doing agent SFT can be extremely powerful, like the Smith paper, but there are still exceptions rather than the common or the norm. So here I want to frame three core challenges that recur across agent data landscape. First, the complexity of data curation. Second, the heterogeneity of dataset formats. And third, the difficulty of analysis and comparison across these datasets. In other words, we have rich data, but it is hard to collect, hard to integrate, and hard to reason about in a systematic way. So ADP later we will discuss about is designed to specifically address these challenges. Let me unpack the first challenge first. Complexity of data curation. Building agent datasets is fundamentally more demanding than collecting static input-output pairs for instruction tuning. We are talking about multi-step trajectories here for agent training, with actions, observations unfolding over time, often in very complex environments and very different environments. The community have explored three main strategies: manual creation by manual creation by human, synthetic generation using LLMs, and recorded agent rollouts from existing systems. Each of these has their own strengths and limitations, and very importantly, each requires significant effort. So it's very difficult to create large-scale training data from scratch. If we zoom in, like manual curation is the gold standard for quality, where humans need to carefully craft demonstrations or step-by-step trajectories. But this is incredibly expensive and oftentimes slow, and requires domain experts, so it's not massively scalable. For synthetic generation, on the other hand, is often faster and cheaper because we can leverage strong LLM to generate trajectories. However, it's difficult to verify the quality and the correctness of the trajectories. And also, synthetic data can lack diversity or realism if we are not careful. Finally, recorded rollouts can give us realistic trajectories from actual agent systems. However, they are fundamentally constrained by the base agent's capabilities and also can propagate let's say propagate wrong or bad patterns from the base models. So across all these three methods of data curation, we still face a trade-off between quality, diversity, and scale. Okay, now let's move to the second challenge, heterogeneity of dataset format. Each dataset defines its own action space and its own observation structure and has their own toolkits. Let's say the datasets we collected for ADP. For example, Mind2Web use the raw HTML of websites. Go Browse might log the accessibility tree structure of the GUI. So any like other datasets might use the screenshots of the websites. Also, coding datasets might use code and runtime outputs in different formats too, and two-use datasets can define their own function call schemas. As a result, like every time you want to use a new dataset with a given like agent framework, you end up writing a custom converter. And if you want to support multiple agent harnesses or multiple datasets, the effort grows very quickly. So in here, I want to illustrate the problem visually. For example, given 6 datasets in 3 agent harnesses, let's say D number datasets and A number of agent formats, such as OpenHand, SweetAgent, AgentLab. Without a common protocol, we need to separate the role to supervised fine-tuning converter for each dataset agent pair. For example, if I want to have OpenHand's supervised fine-tuning format, I need to write 6 converters from each of the datasets to OpenHand format. If I want SweetAgent supervised fine-tuning, I need to write 6 converters again. For AgentLab, it's 6 converters again. So that's like a quadratic effort in terms of the number of datasets times the number of agents we want to convert. So this, after the quadratic burden of the heterogeneity challenge, let's move to the difficulty of analysis and comparison challenge. This challenge is because datasets use very different schemas and conventions, so cross-dataset analysis becomes an apple-to-orange comparison instead of apple-to-apple comparison. Therefore, it's hard to ask like very basic questions like how long are the trajectories? How often do they use tools versus code? How much reasoning did they perform during the trajectories? So this lack of common representation limits our ability to quantify the coverage, the usefulness, and the quality of datasets. And also it prevents us from doing data-driven selection or improvements. We can't really easily say which datasets are most beneficial for a given target task and or where there are gaps in the public ecosystem. Putting these 3 challenges together, complex curation, heterogeneous format, and hard to compare datasets, we end up with a situation where the data exists, but the infrastructure to use it at scale does not. So this here we need a way to bridge the gap between a fragmented agent data landscape and a practical large-scale supervised fine-tuning downstream. So this motivates us the design of agent data protocol. What do we need to bridge the gap? Looking at the challenges and limitations, we propose 3 main design principles of ADP to solve these challenges. First, simplicity. The protocol uses a simple, intuitive structure so that researchers do not need specialized per dataset engineering. It should be straightforward to take a raw dataset, map it to ADP structure, and then immediately start using it for training. Second, standardization. ADP provides a unified representation that can express a wide range of agent training dataset in a single schema. This directly addresses the heterogeneity challenge. Once in ADP, all datasets look structurally consistent. And third, the expressiveness of the ADP. Even though the schema is simple, it needs to be rich enough to capture complex agentic trajectories across coding, software engineering, web browsing, and tool use, with no loss of critical information. This expressiveness is what enables systematic analysis and fair comparison across datasets. Now I will introduce ADP itself. Conceptually, ADP defines a standardized trajectory object that captures an environment and the agent interaction within the environment as a sequence of actions and observations plus flexible metadata. The key idea is that almost all agentic behavior can be decomposed into on the left, the agent takes an action, and then on the right, the environment returns an observation. And repeating this iteratively, ADP encodes these components in a way that is uniform across datasets and environments. So here, each ADP trajectory is represented as a trajectory object with 3 main fields. First, an ID, like the trajectory ID, which is a unique identifier of a trajectory. And second, the content, which is an alternating sequence of action observation objects capturing the interaction. And third, the details, which generally is a dictionary which stores dataset-specific metadata, such as things like source URL of the data, the license of the data, or additional nodes of the data. This separation means that the core interaction logic is standardized, while dataset-specific information lives in the detail field without polluting the main schema. In ADP, action objects represent what the agent decides to do. We categorize actions into 3 types: API action, code action, and message actions. API actions correspond to tool calls, like, for example, in the web page environment, go to an URL, in a browser agent or database query. Code actions capture the generated code snippets and that are meant to be like executed in the environment. And message actions are typically natural language communication, such as explanations, classifications, or final answers to user. These 3 categories cover the majority of behaviors we see across the 13 datasets we convert, while remaining simple enough to implement as like pedantic schemas. So to discuss more details, the schema for an API action is as shown here on the left. It has 3 fields: function, which is specifically the function name of the tool call, and keyword arguments, like a dictionary of arguments, and an optional description, which often includes the agent's reasoning or explanation of why it's calling this tool. For example, web navigation call, like go to of URL of www.google.com is represented as an API action with function name of goto, and keyword arguments of URL equals to https 3w.google.com. Yeah. Next, the code action. A code action includes a language, for instance, Python, Java, like, and then the content, which is the code to be executed, and an optional description explaining the intent behind the code. So a simple snippet like Python print hello world would become a code action with language equals to Python, content equals to print hello world, and the same pattern applies to other languages like Bash, JavaScript, or SQL as well. Finally, the message action captures natural language messages. It has a single content field holding the text. This is used for things like agent explanations, classification questions, or final answer to user. On the observation side, ADP defines two main types, text observation and web observation. Text observations capture textual feedback from the user or environment. For example, user instructions or code execution outputs. Web observation capture the state of the web page, including like HTML, accessibility tree structures, URL, etc. Again, the aim is to keep the set of observation types small, but the expressiveness is enough to cover the majority of agent tasks in our corpus. A text observation has two fields, source and content. The source typically indicates whether the text came from the user or from the environment. The content is the raw text itself. For example, after running the Python code of printing hello world, we might see an execution output like execution result hello world. And in ADP, this becomes text observation with a source of environment because this is an environmental message from the executed output. And the content to be like hello world, which cleanly separates agent actions from environment feedback. A web observation represents the state of a web page. It includes the raw HTML, the AX tree, which is the accessibility tree structure, and the current URL and the viewport size. This is also there's also room to image-based observation, like later if needed. This structure supports complex web tasks such as GUIs, and when agents need to navigate between web pages and reason about dynamic content. It also matched the interface used in benchmarks like Web Arena or frameworks like Browser GM Agent Lab. Now the details. The details field store metadata that is specific to each dataset or trajectory, but not essential to the core interaction schema. Let's say, for example, here we include a source like the Hugging Face URL, a license, which is the MIT license, and the count of trajectories for this dataset, and a short note describing the dataset here. This will allow us to keep ADP generic while preserving information that is important for reproducibility or sourcing the data, attribution, and data documentation. To give a concrete example, on the left, we have the agent logs, the raw agent logs. Like say an URL and go to API call to the URL google.com. The resulting HTML and X tree is shown in the second action, where the web observation is the URL with google.com HTML and X tree located. And another action example is like with the Python print hello world snippet, and the action execution output is here, demonstrated as the text observation. And lastly, the final response becomes a message action. All of these are wrapped into a single trajectory with ID and details. So this example illustrates how heterogeneous raw logs can be normalized into a unified training-ready representation. Now let's look at the ADP conversion pipeline. First, given the raw data, for example, the datasets from agent instruct, codec instruct, 3gen, mind to web. For each dataset, we write a converter that maps the dataset specific trajectories into the ADP schema, like mapping their actions, observations to API action, code action, message action, and mapping the observations to like the environmental outputs to text observations, web observations. And the second step here is converting ADP to agent supervised fine-tuning ready format. So different agent frameworks like OpenHands, Sui Agent, Agent Lab each have their own action space and prompts, system prompts. For each agent harness, we write one single script that takes ADP trajectories and converts them into the harness training format with appropriate system prompts, tool calls, and context management. And after like this pipeline, there's an optional quality assurance, like we can run automated validation checks on each of the data, and we can verify whether the tool call match the expected agent format. We can ensure that most tool calls are paired with a English stop process, like the reasoning process, and checking that the conversation is terminated properly after the conversion. So this helps like to maintain high data quality across the standardized corpus. So let's step back a question, like why we want to convert the ADP standardized data to supervised fine-tuning format for different agent frameworks instead of training a single action model with ADP standardized data. The core intuition behind is that if we want to when the field is crowded with like 100 different agent formats, the natural way is to propose one unified schema. But like if this unified schema is trained as a single action model, then it's just simply the 101st another action model in the field, but not a standard that people will use. So we want to show that ADP can be incorporated very easily to different agent training frameworks. So people in the field, in the research community, could actually use our schema instead of like considering it as just another schema like the other agent formats. Also, we want to make the fact that if we step back, ADP turns what used to be many-to-many tangle into a hub-to-spoke architecture without ADP converting, like let's say there's D datasets in the field, converting D datasets to a number of agents format costs about like 8 times the sum of the per datasets converter code, which is like quadratic in big O of D times A. And if we introduce ADP and the people in the community are using ADP, then each dataset is converted once into the ADP framework, ADP structure, and then each agent framework has a single ADP to supervised fine-tuning converter. So the total cost here becomes O of D plus A, which is linear in the number of datasets plus the number of agents instead of their products, which greatly reduce the effort that community needs to spend in total. So in practice, like across the certain datasets we converted, the raw to ADP converters are a few thousand lines of code in total, where the ADP to supervised fine-tuning converters for these 3 agent harnesses, OpenHands, Agent, Agent Lab, average around a few less than 100 lines of code for each. So adding a new agent becomes very cheap. Just one small script and immediately unlocks all ADP standardized data. If you want to add another agent to the ADP protocol repo, then it's only like taking around average of 100 lines of code. But previously, if you want to add all these datasets to convert all these datasets to a single agent, it might take like thousands of lines of code to convert all the datasets. Another practical impact is that we can now perform apple-to-apple comparison analysis instead of apple-to-orange comparison analysis. So this page shows the apple-to-apples view of the existing agent training dataset once they are converted into our protocol. For each dataset, we can now directly compare the average trajectory length. For example, here we compare the average rounds and distribution of the action, different type of actions, like the API action, code action, and message actions. Here we compare the different types of actions. and the coverage of function slots as well. So for example, we get an average of around 10 rounds of conversation for the trajectories, where we can see that the software engineering ones like SweetGym, SweetSmith has the highest number of average rounds. Also for the actions, let's say for a tool calling dataset like agent instruct, most of the actions are API-based actions, where for the coding datasets, most of the actions are coding actions. For a browsing dataset like Go Browse, Mind2Map, and NetNav, the most actions are API actions because they need to call web tools like go to a new URL and like going through different web pages, etc. And we can see that most datasets have function slots greater than at least 80%. And the average percent of functions that contains a reasoning process is like 83.8%. So these are trajectories that have annotations with explicit function slots, giving us a clear picture of what kind of supervision today's agent already receive. And this could be also helpful if people want to train an agent with reasoning ability. Now let's move to the experimental setup. We evaluate ADP's effectiveness by training agents on a unified corpus that we built from the 13 datasets, covering coding, software engineering, API tool use, and web browsing that we just discussed before. For the base model, we use Queen 2.5 coder instruct for all the sizes, and the model sizes will cover are 7B, 14B, and 32B. For each size, we fine-tune separate agents for 3 agent harnesses, OpenHand, 3 agent, and Agent Lab. All models are trained using the same supervised fine-tuning pipeline from Llama Factory. For evaluation, we used 4 benchmarks: SweetBench, Verify for software engineering, WebArena for browsing, AgentBench for coding, and Gaia for tool calling. And the references and citations are included in this page as well. Our results is that ADP fine-tuning consistently improves performance across models, benchmarks, and agent harnesses, often reaching state-of-the-art or near SOTA performance for models in the same size range. For example, the plot plotted here is the results. Like the upper trends here are the results for the trained model, and the lower lines here are the results for the base models. For example, for a 7B model, the result on SweetBench is around 20%, whereas the non-trained base version on SweetBench is 0.4%. Similar trends follow for the other benchmarks as well. These gains show that unified cross-domain ADP training corpus can produce highly effective agents without any domain-specific tuning for each benchmark. Okay, another natural question is, like, should we just fine-tune on a single task-specific dataset for each target benchmark, or does mixing diverse ADP data actually help? We compare 3 settings for here, no fine-tuning, so the base version, task-specific only fine-tuning, like we fine-tune only SweetSmith on OpenHands and test on SweetBench, and ADP mix data, which is our cross-domain corpus. Across SweetBench, WebArena, AgentBench OS, and Gaia, the ADP mixture consistently outperforms task-specific tuning on the target benchmark. For instance, on SweetBench with an OpenHands agent on the top, training on SweetSmith only yield like about 1% accuracy, and training on the full ADP data achieves around 10%. This is with the Queen 2.57B instruct model. And then, like similarly for the Queen 3AB model, the results is also higher when training on ADP mixed data. WebArena, like when training on only one single dataset group rows, we achieved 16%. We are training on the mixed ADP data, we got 20%. Yeah, so we see a similar pattern across here. ADP yields better in-domain accuracy and stronger cross-task generalization. So diverse ADP data not only avoids catastrophic forgetting, but actually improves performance relative to single domain SFT. Another practical impact is that ADP eases adaptation to new agent harnesses. When we think about future agent frameworks, ADP makes it dramatically easier to adapt to new agent harnesses. Without ADP, which is the blue line, each new harness will require re-implementing converters from every raw dataset into the harness SFT format. With ADP, which is the orange line here, a new harness only needs one small ADP to SFT converter and instantly gains access to the entire ADP standardized corpus. So as a conclusion, to summarize, ADP provides a practical, lightweight interlingua for agent training data. By standardizing actions observation across heterogeneous datasets, ADP turns today's fragmented data landscape into a scalable training pipeline. ADP also reduces community effort by collapsing what used to be a quadratic O of D times A engineering problem into a linear O of D plus A engineering effort, where each agent harness only needs to be integrated once. Empirically, training on ADP yields monotonic gains across model sizes, agent harnesses, and benchmarks, achieving state-of-the-art performance or near state-of-the-art performance in multiple domains. So looking ahead, we see several immediate directions. Like first, multimodality, extending ADP beyond text and HTML to include images, screen recordings, and potentially other modalities as well, so that we can capture richer agent environment interactions, including desktop or more GUI, like visual GUI-based agents. And second, standardized evaluation. We can apply the protocol idea not just to training data, but also to evaluation environment interfaces, so that datasets, agents, and benchmarks compose more cleanly if we have standardization for all of them. Thirdly, the community growth and data quality is also important. Continuing open source releases, like strengthening automated validation and exploring semi-automated dataset conversion pipelines so that ADP can scale while maintaining high quality is also important. If you would like to explore or build on this work, these are some useful resources that we publish. The full paper is available on arXiv. The website contains a mini conversion demo from the agentdataprotocol.com. You can see live demos of like how to convert dataset from the raw format to standardized ADP format and then to downstream agent formats. And then the GitHub repo contains the ADP schemas if you want to check the details, the written converters, and the trainings, and the scripts. All of these are released openly, so the community can add datasets, improve converters, and try new agent harnesses. Also, a call for action. Feel free to add your favorite agent training dataset to our repo. The instructions are available here on the GitHub repo. If you have an interest in adding a conversion script for your favorite agent harness, please do so. We have like 3 agents supported right now, and we welcome more support. And finally, if you are training agents, we'd love to see you train an agent using ADP. Share your results in the community and help us refine and extend the protocol. Okay, thank you. That's all I have for today. Thank you so much for listening. I'm happy to take questions about the protocol design, the datasets, training, or how to like plug in your own system to ADP. And also thanks the NICE platform for hosting this talk.
Great. Thank you, Yueqi, for this very interesting work and the very interesting talk. So yeah, so here's the QA. So there are several questions. So one is that have you identified the generalization challenges for, I think, two-use SFT, two-use supervised fine-tuning across different agent scaffolds, toolkits, or task domains?
The generalization, yes. In it's for example, in our main training experiments, like more results could be found in the archive paper, but like here we demonstrate several selected results for um, different agents on different benchmarks. So our ADP data could work on agents like OpenHand, Agent, and Agent Lab, which are very different in terms of tools. For example, OpenHand contains 7 main tools, if I remember correctly, which include browsing, coding, thinking, and file using, etc. And for Sui agent, there's like only 3 main tools, which are batch execution, file localization, and submit, which is submitting to the Sui bench. For Agent Lab, there's a ton of different tools, like basically GUI based, like go to a different URL, click and type, etc. So our ADP framework works for all of these 3 different agent setups and on the 4 benchmarks. So we believe that with our current experiments, we could demonstrate that ADP is generalizable across different domains and agents and benchmarks.
Okay, so I think one follow-up is like, is there any like issue for generalization of combining two set configurations?
Sorry, could you repeat the question?
Yeah, I'm also a little bit confused. So like the generalization of combined two set configurations.
Uh, Do you mean like training a model that is able to, for example, work for both OpenHand Sui agent and Agent Lab? We are actually considering this as a follow-up experiment. We are currently waiting for GPU allocation to have like this experiment done.
Okay.
Yeah, we will see what happens after we train this model.
Okay. Another question. So besides actions, how should we arrange the thinking trace?
So in our standardized schema, we include thinking traces here. In each action, we include a description field, where this is essentially just the function thoughts or reasoning process of the agent trajectory. So this field is incorporated such that if you want to train a reasoning model, like these could be extracted and specifically encoded in the thinking traces.
Okay. One follow-up. So I think there's a picture where there's a table where you show the data set, average rounds, and function thoughts. So I was wondering like why for mind to web, the function thought percentage is 0?
Oh, I think the Mind2Web does not provide function thoughts in their openly released datasets on Hugging Face, so it's 0. But like we also, in our toolkit from ADP, we incorporate a script that could allow you to generate function thoughts using reasoning models. For example, in actual training, we actually generated function thoughts using O4 mini.
I
And then
see.
incorporated the function thoughts for, yeah, for example, Mind2Web switch with lower function thoughts percentage.
I see. Okay. Okay, another clarification question, I think. In page 26, so what are the base models?
Oh, the base models are Queen 2.5 coder instruct. Um, and the sizes of the model are labeled in the x-axis.
Okay, cool. Yeah, so um another question. So so I wonder like how is the converter implemented? So for example, I think for some data sets, you have the original traces and then you use a converter to convert it into like this ABDP format. So like how is the actual like converter implemented?
The actual converter, like some parts are implemented by the authors, some are like community efforts. But like basically for each trajectory, there is oftentimes a given pattern of a trajectory.
Mhm,
And let's say in the raw data, a trajectory like this
mhm,
is converted to a set of iterative action observation trajectory, where, for example, the go-to action is converted to an API action. The results of the web page is converted to a web observation. Um, yeah, so users were, when we wrote the converters, we wrote like um, rule-based converters where we convert like different types of actions in the raw data to different types of action in ADP and converts observations from raw data to observations in ADP as well. So, but basically all are rule-based.
I see, I see. Yeah, I was wondering like can there be any LLM judge or like LLM based converter? Then that's like super expensive and slow.
Yeah.
Um,
We in the datasets we currently support, we don't need LMS a judge, but I'm not sure about like other datasets. Maybe in other datasets where rule-based conversion might not work, then LMS judge could like be a good substitute.
okay, okay. Um, so another question, so in this ADP, so is there any like special design choices? Because in general, this ADP sounds like pretty generic. So is there any special design choices that you make that you decide to use when your team like design this ADP?
Design choices. We did iterate like a lot of runs to make sure that ADP could cover everything that we want for the datasets. Let's say at first API action is not included in the design of ADP because like at first we experimented with datasets like code feedback, codec instruct, Swiss which are mostly coding datasets that does not require API calling. But later when we incorporate the browsing datasets like Mind2Web, Go Browse, then we need to incorporate the API calls so that we could represent web browsing actions as well. So uh, yeah, so this design choice is like iteratively refined. And later we might expand this ADP schemas as well. Let's say as I discuss here for what's next, we want to extend ADP to support multi-model inputs and outputs. Then like we need to include like for example for image observations, we could extend the observation field with like an image observation that could support multi-model inputs.
Mm, okay, okay. And then would there be any issue of backward compatibility if you extend this?
Um, for example, for the current setup in ADP, we convert the data sets to OpenHands reagent and agent lab conversions. Um, So if like if adding image observation in the new ADP schema, these scripts need to be updated to incorporate the new code to process image observations as well.
Oh, I see. So I see. So if you add this multimodal, um then of course like you need to change this converter, but then the previous like the data that's generated previously, do you think we need to abandon them or like update them in some way?
There's no need to change the previous data converted because like for example for um, agent instructs, there's no image understanding or image grounding questions.
Mhm,
So there's no need to add image observations to existing trajectories that we
mhm.
already converted to ADP format. We only need to um, update the scripts to convert ADP format to agent-specific formats to include the new image observations.
Okay, okay. Um, Another question. Okay, so I think still like again in page 26. So so there's a comparison with the baseline. So for the base model, so this base model is like the Quan is not trained at all on any agentic data.
Yeah.
I see. Okay. So it's not like comparing with Quan that's trained on like non-ADP, like heterogeneous data, and comparing it with like Quan trained on ADP data.
No, but like in the paper, it includes results, for example, from the Sweden paper, where Queen 2.5 coder instructs to train on the Sweden data set and then evaluate on OpenHands and then on Bench. So we compare with other trained models as well. We just didn't show it here because there are 3 large tables that showing performances.
I see. But okay. Will there be any issue if we train on very heterogeneous data? So I guess the main issue would be like how you generalize to a new agent framework. Like yeah.
So do you mean heterogeneous in terms of the format or in terms of the task?
Format.
Yeah, let's say, for example, agent instruct here is in because for example, for agent instruct, the authors develop agent instruct and train on agent train to achieve agent LM. So the format here for agent instruct is very different. They have very different system prompts, different tools that are incompatible with, let's say, a downstream agent like OpenHands. So if we train a model directly on agent instruct without like converting the format to, let's say, OpenHands format, then like the model just like learned agent instruct to calling format and could not adapt to OpenHands to calling format. So training on heterogeneous data sets would not work, at least for open source models.
I see. So in some sense, those based model is not so good at generalize different formats because like usually the formats is also specified in prompts.
Yes.
I see. Okay. Another question. So so is this ADP mainly about switching between different system prompts?
No. Let's say um let's say the conversion, like for example, the agents here, OpenHands, Agent, Agent Lab has very different system prompts. So the script to convert ADP to supervised fine-tuning format needs to like adapt the system prompts to specific agents. But for converting the data sets to ADP format, the system prompts like from the original data sets is sometimes preserved as the first user message where the task query is included. So ADP does not provide a standard system prompt. ADP is only a schema that represents the original data. It's not a new like agentic format that includes system prompts.
Okay. Okay, so it's basically like it's mostly a conversion for formats instead of actual contents, including like system prompts. Okay. Yeah, I think that's that are all the questions that we have for now. Yeah. So thank you very much, Yueqi, for this very cool presentation, and like thank you all for this very interesting and active QA session. So I think this is the end of today's presentation. And you can scan the code for WeChat and this nice Discord if you have any further questions that you want to discuss offline with Yueqi or anyone else. So yeah, thank you again, everyone. This is for today.
Thank you.